Hi guys, welcome back. This is the last video in YOLO-V4 model. In the last few videos, we discussed about the model architecture in detail and also discussed about the bag of freebies and the bag of specials techniques. We have covered the topics which are highlighted here in the boxes. In this video, we will cover the remaining topics which are mostly related to data augmentation and training methods. So we will cover these topics now. So let's start with data augmentations. What are exactly data augmentation methods and why do we need them? Basically, data augmentation methods are a way to increase the dataset. So either increasing the volume or increasing the variations in the data. So we modify the existing dataset, in this case the images and annotations, to increase the dataset size and also the diversity of the dataset. Why do we need this in the first place? This actually helps the model generalize better and become robust to the real world deployment. Suppose you are having very few number of images and those are not enough for your training and you are not able to collect more dataset, then you can use data augmentation methods to increase the volume of your data. At the same time, if you are having the images which are looking very similar and you want to create different views of the same object so that the model can learn and generalize better, then also you need to use data augmentation. Basically, all the data augmentation methods can be categorized into these three categories: photometric distortions, geometric distortions, and object variations. Photometric distortions is all about adjusting the pixel values. You are not changing the position, you are only adjusting the pixel values, you are only adjusting the image appearance, like adding the noise, modifying the brightness, contrast, hue, etc. All of these come under photometric distortions. So these distortions only affect the image appearance. These distortions won't affect the object shape or size in any way. The second category is geometric distortions. Geometric distortions are actually affecting the position or shape of the image or object, etc. Some examples are flipping, rotation, scaling, cropping, all these things. So these are very basic operations on modifying the image. And the third category is object variations, modifying the image at object level. So maybe you are randomly cropping out some portion of the object, you are removing that and placing in some other images, or you are masking some portion, or you are clubbing multiple images together to form a single image. All of these come under object occlusions category. You can see the examples here. This is my original image, and if I flip that image, the dog is facing this side, now it is facing towards the right. And I cropped certain portion of the image, that is actually cropping, and I have shifted the image to the top left, that is translation. Similarly, I rotated the image by certain degrees, that is rotation. And here I cropped certain portion of the object, that is actually erasing or cutting out. So these are some examples of geometric transformations, and these are photometric transformations. So you are increasing the brightness, hue, saturation, contrast, blurring the image, at the same time adding some noise. So all of these come under photometric distortions, and these are geometric distortions, and this is like object level modification, removing some portion of the object, and you are asking the model to identify that it is a dog based on only these features. So if you see here, I have only one image. From this image, I have created 10 more images and added to my dataset. I can use all of this data together for training the model. Now we will look at the augmentations which are majorly used in YOLO-V4 model. Most of the deep learning pipelines already use these kind of basic augmentations like blurring or adding noise and these geometric transformations, but YOLO-V4 added some more augmentation methods for the object detection task. Let us see them one by one. One such augmentation is Mixup Augmentation. This is nothing but taking the pixel values from two images and clubbing them together into a single image based on a value called lambda. So here lambda can be 0.52. From the other value, it will be 1 minus lambda. So it will be 0.48. So for every pixel value, I multiply with 0.52 from this image and I multiply with 0.48 from this image, and whatever the resulting value, I will keep it in the final image. So if you see, the shapes and size of the images are same. Okay, so I took lambda as 0.52 here. Automatically from the second image, I will take 0.48 weightage. Now you have modified the image. what about the labels? What label should I give for this image? So for this image, label is dog. For this image, it is cat. But what about this? I can give both dog and cat. I can give dog as 0.52 and for cat I will give 0.48 as the target value. This will be my ground truth target. So this is how the mix-up augmentation works. Similarly, Cutmix is another type of augmentation. This is very simple. You randomly crop certain portion of the image and you paste it here. That's it. So either you crop from here and then paste into this image, or you crop from here and paste into this image. The final image will have two objects, and you can actually adjust the bounding boxes as well based on the final image. So here, if the bounding box is like this, the same will be adjusted like this here, right? Similarly for this object also, the bounding box will be adjusted like this. Okay. So this is Cutmix augmentation. And one more popular data augmentation method is Mosaic data augmentation. This augmentation is introduced first time in YOLO-V4 model. This is nothing but clubbing 4 images into a single image. So if you observe here, every image is consisting of 4 images, right? You can see that this is the distribution. This is one image, this is the second, this is the third image, and this is the fourth image. Similarly, for this example, this is the distribution. So every image consists of 4 images here. So you are clubbing 4 images into a single image and then sending that as an individual example to the training. So this is like a 4x4 grid. How is this helping the model? How this kind of clubbing multiple images together helping the model in improving the performance? So basically, by merging 4 different images, the model learns to detect the objects in different backgrounds. From the model side, it thinks this total is a single image, and it sees a person here, it sees multiple persons here, and it has different backgrounds. Single image has different backgrounds. So it helps the model to generalize better based on these diverse backgrounds. If you take wild animals as an example, usually wild animals appear in the forest background. So whenever there is a forest background, it assumes that there can be a wild animal over there. By using this mosaic augmentation, we are removing that bias in the model. This augmentation is majorly for object detection tasks. So if you have multiple objects also, your bounding boxes will be adjusted according to the merging process here. So the bounding boxes will be automatically adjusted and kept it like this in the final image. Okay. So this is actually mosaic augmentation. So this is the final list of augmentations YOLO-V4 has used. So the common flipping, rotation, cropping, all these are there. Along with that, Mixup, Cutmix and Mosaic are the major augmentations it has used. The next bag of freebies YOLO-V4 has used is random training shapes. This is a very small tweak which has improved the model accuracy without affecting the performance of the model or without any computation overhead. In simple terms, using random training shapes is nothing but dynamically selecting the shape of the image during training. That means during the training process, for every batch, you load few images and you select one of the provided shapes as your final shape and you resize all the images to that particular shape. Suppose in this example, I selected 512 as my batch shape. So I will resize all the images for that batch into 512 and then I will use that for the training. In the next batch, I might consider 608 and I will resize all the images to 608. So this is almost similar to multi-scale training. You are providing a range of size values into which the images can resize during the training. So it randomly selects one of these for every batch and automatically reshapes all of them into that particular size. There is one more addition to it, which is dynamic batching. Suppose you have a GPU of 16 GB and if I take the size of 320 by 320, I can fit 10 images, suppose, into this 16 GB memory. When I pick 320 as the training shape during training, I will adjust the batch size also to 10. If I pick 608, I might keep only 5 as the batch size. So this is actually dynamic batching. So there is no fixed batch size during the training. You are dynamically deciding the batch size based on the image sizes. So if the image size is small, you can fit more images into the GPU memory. So your batch size can be high. But if your image size is high, then you can fit only less number of images. So this is actually dynamic batching. Let's see with an example. Suppose these are your preferred sizes. So during training, for every iteration, you select randomly one of these. So for a particular batch, you selected 416 by 416. And then batch size is set up as 32, assuming that this 32 images of this particular size can be fit into your GPU memory, right? So all the images are resized to this and training will proceed. In the next iteration, maybe 5 and 2 might get picked and all the batch size will be adjusted accordingly. So this is how random training shapes and dynamic batching works in YOLO-V4. The next concept in bag of features is the use of multiple anchors. Usually when we use anchor boxes for the prediction, we assign one anchor box to the ground truth based on the IOU value. So you have multiple anchor boxes, but you decide the final anchor box which corresponds to that ground truth value based on the IOU calculation. Whichever is having the highest IOU with the ground truth, you will decide that. But in case of YOLO-V4, what they have done is they keep all the anchors which has the IOU greater than the threshold. So instead of taking the highest IOU value, you keep a threshold, maybe it is 0.7 or something like that. So whatever boxes have IOU greater than 0.7, they will keep all of them and they will perform the loss calculation for all of them. Okay. In this way, for a single ground truth box, you can have multiple anchors learned for that. Okay. So all of these might have an overlap greater than 0.7. So we'll keep all of these boxes and we will calculate the loss based on this adjustment for bounding box as well as classification. So it improves the model capability and also it speeds up the training. It can help in handling different object sizes because you are trying to learn the ground truth from different anchor box sizes. And the next concept is label smoothing. This is a very well-known concept in neural network trainings, usually classification task. So what is exactly label smoothing? Suppose you are training an image classification model with these categories. 5 classes: cat, dog, horse, tiger, lion. These are the categories. Usually the ground truth we represent in these formats. This is actually one hot encoding vector. Suppose for the first image, your label is tiger. 0, 1, 2, 3, fourth position. So the fourth position will be 1. The remainings will be 0. This is your target value. Similarly, for the second image, cat is the label. So it's in the first position. First position will be 1, others will be 0. So these are nothing but one hot encoded vectors. So these are there in data science as well. So this is very famous technique to convert any categorical variable into the numerical representation. Now, instead of giving this, why don't you give this format as the target? So let's assume that in case of tiger, this is the position. Instead of giving 1, I gave as 0.9. The remaining 0.1 I distributed across the remaining 4 indices. Similarly, for the second image, category is cat. So the first position will be 0.9. Remaining all will be combined together 0.1. Right? So it can be 0.8 and 0.2 as well. So you can decide how much smoothing you want to do. Okay. So instead of giving 1 or 0, we give the smoothed values. That's it. But why do we need this in the first place? Why don't we give one hot encoding vectors like this? Why should we give these values if it is not that particular category? If it is not a cat, why should I give some weightage here? It actually helps in preventing overconfidence in the model. It also helps in calibration process. There is a concept called calibration of the probability scores in image classification. Basically, if a model predicts an object, it usually says it is a cat and the value will be 0.9, suppose. So this means that the model is confident that it is a cat and it is 90% confident, right? But what is the guarantee that this number actually indicates how confident the model is? Maybe the model is only 80% confident, but the output it is giving 0.9. So there is a calibration error of 0.1, right? So this is what the calibration is. By using label smoothing, we can actually improve the calibration. So that means if a model says 0.9, we are sure that it is 90% confident. Also, it enhances the regularization. It actually mitigates or reduces the impact of noisy labels. Suppose you have one mistake in the labeling. It is actually a cat, but you gave as a dog. So if I give 1, 0, 0 like this as labels, we are saying the model that I am damn sure that it is a dog, it's not a cat. But if you are giving like this 0.8 and maybe 0.5, 0.5, 0.5 and 0.5 like this, then we are saying that we are 80% sure that it is a dog. So we are not 100% sure. That is where it prevents the overconfidence. So if there is any issue with the labels as well, if there are any mistakes in the labels as well, this actually reduces the impact. It will not completely solve the problem, but it reduces the impact. So we saw that instead of giving 0, 1, 1 like that, we can give these smoothed values. But how do we get these values? We should do this automatically during the process, right? That is based on this. So there is a smoothing parameter which is alpha. Suppose alpha is 0.1. Okay. Then the total number of classes in the previous example is 5. So I can get for the actual class, suppose for the actual class 1, 0, 0, 0, 0. This is the one hot encoding vector I have. So for the actual class, that means for this where 1 is there, the output will be 1 minus of 0.1 plus 0.1 divided by 5. 5 will be the number of classes. Whatever value I get here, this will be my actual value. So this is actually 0.9 plus 0.1 by 5. That means 0.02. So this is actually 0.9 plus 0.02. So this will be 0.92. And what about the remaining zeros? In all those cases, the value will be alpha divided by C. That means this value 0.02, 0.02, 0.02, 0.02 and 0.02. So this will be converted as this automatically based on this formula during training. So this is how label smoothing works. Label smoothing is actually implemented as a part of the loss function itself in almost all the frameworks, whether it is TensorFlow or PyTorch. The categorical cross entropy, the cross entropy loss itself is having a label smoothing parameter. You just need to provide this alpha parameter here and it automatically applies the smoothing to the labels while doing the loss calculation. Okay. The next concept in bag of freebies is learning rate scheduler. YOLO-V4 uses Cosine Annealing LR scheduler. Basically, a learning rate scheduler is used to adjust the learning rate in the optimization process. So during training, we have to adjust the learning rate as the training goes. We typically start with high values and then we reduce the learning rate over the time. So it all depends on the type of learning rate scheduler. Cosine Annealing learning rate scheduler follows this particular pattern. We provide the starting learning rate and the minimum learning rate it can go. So you can see that maximum learning rate and minimum learning rate here. We also mention in how many epochs the learning rate should reach the minimum value. So that means from maximum to minimum, you have to go down in how many epochs. So that is this parameter, steps, cycle steps. So one cycle should take 10 steps. So if you start here, it should reach the minimum value within 10 steps. Again, next start to minimum, again 10 steps. So every cycle is of 10 steps here. Now it has started here. It has reached the minimum value within 10 steps. Then after 10th step, it reset the value. How did it finalize this value as 0.7? That is based on this gamma. So gamma is equal to 0.7. So gamma value decides what should be the new maximum value after every cycle. Okay. So the gamma you multiply with the existing or older learning rate. Suppose I have a learning rate of 1 here and after 10 epochs, I should multiply 1 into 0.7, which will give me 0.7. So that should be my new maximum learning rate. So this is 0.7. And then I continue still 20 epochs and it reach the minimum value. Now at 20, I need to reset again. So what should be the new value now? It should be 0.7, whatever the older value, into this gamma, which is 0.7. So this is equal to 0.49. So that's why this new value will be 0.49. After the another 30, it will reset to 0.34 like this. So it always multiplies the old learning rate with gamma and then it gets the new set value. So it continues like this. This is the learning rate scheduler used in YOLO-V4 training. The next caveat in the YOLO-V4 training is using genetic algorithms. Genetic algorithms is completely a different concept. I don't want to go deeper here. I'll give you the high overview. In YOLO-V4, for finding the optimal hyperparameters, they used genetic algorithm. What are hyperparameters? Hope everyone knows what are hyperparameters, right? So there are some parameters you need to decide based on your data set for training, like how many epochs you want to train, what is the batch size you should keep, what is the learning rate value, initial value you should keep, or if you are using any weight decays or momentum values. All of these are actually hyperparameters for training the model. You decide these values based on some heuristics because you are aware of your data set and how many epochs you want to train to reach high accuracy, you might estimate. Okay. Or if you don't have any idea, you will try randomly few iterations with different variations, right? Maybe you start with 10 epochs and you observe that the loss is still going down. So you might need to train for some more epochs. So you will increase to 20 epochs or 30 epochs. Similarly, batch size you can decide based on the GPU memory capability. So like this, you will try different combinations and you will finally find out the best value which works for your dataset. So this process, if you are not very experienced and if you are not able to make heuristics, then it is very tedious and time consuming. And sometimes you might not be able to get the best value also. You might train with some value which is working fine for your case, but it might not be the best one for your dataset. There are many methods for finding the optimal hyperparameters. So there are packages or toolboxes which can do these tasks like Optuna, right? So one such thing is genetic algorithm. So genetic algorithm is used to finalize the best hyperparameters in case of YOLO-V4. So how does it work? Genetic algorithm usually it is coming from the evolutionary algorithms. Basically, it is like you take some set of chromosomes and you perform some task, and based on the rewards or how well they are doing, you just make some permutations and combinations of those and create a new offspring. So these are some terms actually: chromosome, offspring, reward, like this. These are some terms in genetic algorithm. Suppose I want to find the best hyperparameter values for learning rate, batch size, momentum, or IOU thresholds, etc. I will keep the minimum and maximum limit. Suppose learning rate I want to go till 0.0001 and maximum limit I can go till 0.1. And batch size I can go minimum 4 and maximum maybe 64, something like this. Weight decay I want to keep minimum 0.0001 suppose, and I can go maximum 0.01. IOU I want to go minimum 0.3, maximum I can go 0.8 for suppose. So these are the parameters I want to optimize, and these are the ranges. So first we defined what are the parameters you want to optimize and what are the ranges for those parameters. Now we need to randomly select a value for each of these from this range, and that we call it as a chromosome. So I am selecting one chromosome which is a combination of all these. Suppose I decided I will keep learning rate as 0.001 and batch size I will keep 32. Decay I will keep 0.0005 and IOU I will keep 0.5. This is one chromosome. So this is LR, this is batch size, this is weight decay, and this is IOU value. So this is one chromosome. Like this, I randomly select 20 or 30 chromosomes, suppose. So 20 chromosomes. And then for all these 20, I will actually train the model and then I will evaluate the model. And based on the MAP value or mean average precision or precision recall, whatever metric you want to finalize on, okay, suppose I want to finalize or maximize the MAP. Now I have decided that I will take out of these 20, I will take the top 2 performing chromosomes, which is giving me the highest MAP. Now with these top 2 values, I will perform crossover. Okay, so out of the previous process, I got 2 chromosomes, which is giving me the highest MAP. So these two are my best combinations which give me the highest confidence score. Now what I do is I create a new offspring, a new child from these 2 parents. So we consider these as parents and we create a new child from these 2 parents. This we call it as crossover process. So now with this, I will create a new child which can be 0.001 and 16. So I used batch size from the second parent. Maybe I will use this and I will use this 0.0005 and 0.6. So this is my new child now. Similarly, I will create multiple childs from these parents with different combinations of this. So this is actually child 1. This is actually parent 1 and parent 2, suppose. After this, I will perform mutation. So there is a concept called mutation also. Mutation is actually random combination. Instead of taking this value, which is the combination of these two parents, I want to add some more randomness. So this one I will increase to 0.002. Remaining I will keep the same. This is actually randomness. So this process is called mutation and this is my final value. So I will train the model again on this final value. Similarly, I will create few more. Like this, I will create maybe 10 chromosomes this time. So with these 10 chromosomes, I will train the model again. I will evaluate the model and then whichever chromosomes performing the highest MAP value, I will finalize those. So this kind of iteration I can actually do for maybe 100 iterations or 20 iterations like that. Or I can decide what is the MAP value I want to reach. So till I reach that MAP value, I might continue this one. Let's say I want to reach the MAP of 0.9. Till I reach 0.9 MAP, this process, the whole process, randomly selecting, training, evaluating and selecting the top values, creating a child from that, all this process continues till I reach either of these criteria. So this is actually genetic algorithm process. So there are tools for doing that. Genetic algorithm. There is in Python also distributed evolutionary algorithm. There is a package for that. You can actually use that in Python to do that. Okay. The genetic algorithm is used to find the optimal hyperparameters in YOLO-V4. Yeah, here I explained the same process. First you define the hyperparameter values and then you decide one chromosome which is a combination of these values. Okay. And you create initial population, maybe 10 or 20 values by randomly selecting these. You train the model. So this is actually fitness function, which is training the model and evaluating like MAP value, all that. And finally, top performing hyperparameters you will decide and you will cross over. That means you combine these hyperparameters, top performing values and create new set of values. Once you create new set of values, you add random changes so that you maintain the diversity. Finally, with the new generation, you actually repeat the process again, fitness function, again train it, evaluate it, all of those things. So finally, once you completed the fitness score, like when you see that there is no more improvement over there, over the MAP values, or you have crossed some generations. Generations means iterations here. Maybe you did this process for 10 iterations and you found that, okay, we are reaching a saturated value. So then you will take the final value as the best hyperparameter and then use it for the training. The last and final technique in freebies is self-adversarial training. Before going into the details of self-adversarial training, let us understand adversarial attacks. So what are adversarial attacks? Adversarial attacks are actually the techniques used to fool the machine learning models. So remember this, it is actually fooling the model. If you see the example here, this is a classification model. You gave this image and it predicted as panda with 57%. And then what you did, you added some noise. Okay, some noise you added. How did you get this noise? We will discuss. Some noise you have added and you gave the resulted image to the model and it predicted as gibbon with 99% confidence. So you actually fooled the model by adding some noise in the data. Usually this noise is not visible to us because for us it looks the same, but the model actually fails to identify that. So this is actually an adversarial attack. These are carefully crafted modifications. This is not some random noise. This noise is also decided based on the model. There are many types of adversarial attacks like white box attack, black box attack, physical world attack, like that. So white box attack is basically when you have the access to the model architecture also. You have the model and you want to fool that model, you can do that using white box attack. If you don't have the model details, then you call that as black box attack. Basically what they do is, you have the model here and you have certain image. You pass that image and you got a loss value. You adjust this value, you add some noise to this so that this loss is increasing. In gradient descent, what we do, we try to minimize this loss value, right? You adjust the parameters of the model to minimize the loss value. In the similar way, to maximize the loss value, what you need to add to the data? So that noise you can actually calculate so as to maximize your loss. So this is how the noise is decided, and that noise is used for modifying the dataset so that your model will fail because the loss is increasing with that noise. That means the model is failing. So this is a simple concept of adversarial attack. Now, self-adversarial training is actually a defense mechanism against these adversarial attacks. So basically what we do is, whatever is happening here, the loss calculation and trying to maximize it, this process you do during the training itself and add that noise to the data and use the data to train the model. So that means whatever adversarial attacks possible for that model and for that data, you are synthesizing them during the training process and you are training the model to be robust against them. That is nothing but self-adversarial training. Basically it goes like this. Model is initially trained on the clean data, okay, whatever original data set you have. Now during this phase, for every iteration or maybe at certain intervals, the model predictions are used to generate the adversarial examples, okay, by slightly perturbing the input images, by slightly modifying the input images. This is done by maximizing the model's prediction error, that means maximizing the loss, while your modification should be within a limit because they should be very subtle and realistic. That means it should not be identifiable from the human eye. Okay. Now what happens when you made these modifications to the image? In the next phase, you take these examples, whatever the modified examples, as inputs for the training. Now the model is trained to correctly predict the object even though the images are modified. Okay. So then the model will be robust against the adversarial attacks. So this is self-adversarial training. So it's a very simple concept. One additional step you are doing. It is similar to your hard negative mining, right? Usually during the model training process, you mine the hard examples. So basically where the model struggles to classify, those examples you take and you train the model in the next iteration with those examples, giving more weightage for those. In the similar pattern, you predict on the original image and then you add some noise to the data so as your loss will increase, and then use that new data for training the model again so that you are making the model robust against these attacks. Okay. So this is very simple concept, self-adversarial training. So this is used in YOLO-V4 training as well. Okay. So this is not anything to do with the model accuracy improvement or anything. This is to improve the model robustness against the adversarial attacks. That's all from this video. We have covered all the concepts in YOLO-V4. Okay. Thank you.